Hello, everybody, and welcome to the final stream of Advent of Code in Kotlin 2024 edition. Wow. Time flies when you're waking up at 6 a.m. every morning and doing puzzles, if you ask me. If you decided to join us again for the stream, say hello in the chat and drop us a couple of lines about how you felt about today's puzzle. I really appreciate all of you sticking around with me for these 12 days. It was a very fun trip, and I'll be quite honest with you, I think a lot of these puzzles are very much elevated by the fact that we get to discuss them, and that you get to drop some suggestions in the chat. We get to talk to some guests. We get to go down weird side quests about benchmarking, language design, the visualizations, lambdas with receivers. I don't know, pretty much everything. So yeah. I already see that we have a whole bunch of people tuning in again, which is a real delight. Yeah, it is the last day of streams. It's bittersweet for me here as well. But I will also be quite honest. I also need a break every once in a while. I might want to go out to Christmas dinner with people at some point. Link up with some family. So while I might still tinker around with some of the upcoming challenges, and of course I encourage you to do the same, we're not doing the full schedule anymore. But do not fret. The community lives on. Because if you haven't seen this part yet, we have the Advent of Code Slack channel in the Kotlin Lang Slack, where you can find for every single day a discussion with spoilers, without spoilers, where you can exchange ideas, where you can see other people's algorithms, where you can ask people how they managed to solve it so quickly, and you might even get an answer back that's not just intuition, maybe. I don't know. Yeah, so I'm gonna drop a link for that as well, and I would very much encourage you to join. If you are not yet in the Kotlin Lang Slack, there's a join Slack button up here, and within about 48 hours you are going to get an invitation, and you can just join. There's a lot of people here. You could have a lot of great conversations. Let's take a quick look here at some of your notes. Can't believe it's the final stream. Yeah, it goes over so quickly. But you have 12 of them. So, if you missed one of them, make sure you head on over to youtube.com/Kotlin, and under the live tab, you can catch up with everything. Whether it's visualization stuff, whether it's, with the core ecosystem lead, with our language designer, everything. You get to look at some gorgeous thumbnails that were clearly under-edited. Here's a fun fact. I really thought they were going to put a Christmas box into my hand for this one. Or, replace the login screen on my computer with something a little bit more festive. But I guess Sebbies can't be choosers. I don't know. Let's see here. I solved part 1 and part 2 test cases, but couldn't get the right number for the part 2 real data set. That's always tough. Part 1 was pretty straightforward, and then I struggled with part 2 until I drew stuff after over 1 hour. I'll be honest with you, 1 hour, that's still pretty reasonable. You don't want to know what my numbers look like today. Well, but I will. That is unaltered. That's how you know you're getting the real deal here. That's just me. No cheating involved here. Yeah, I realized today that I haven't tagged my repo appropriately yet. What a rookie mistake. Martin, and as my colleague, no less. Of course, what Martin's talking about is one of the aspects that we mentioned in our Advent of Code 2024 in Kotlin blog post. You know this by now. You've tuned in before. But if you haven't yet, there's a way to win prizes. Either you can join the leaderboards and you can compete for top spots. You can join the leaderboards and just kind of hang out and compare yourself. As long as you solve a couple of things, there's still a chance that you can win something. And of course, if you solve a couple of challenges, you throw them up on GitHub and tag your repository with the AOC 2024 in Kotlin tag, like those other 879 folks. You also have a chance to win something. And you also have a great way to, first of all, get your own repository discovered, and for you to discover other people's repositories. So make sure you take a look there. Yeah, Jonathan says, I beat you today in solving it. Yeah. Today was lovely, wasn't it? Which is really yeah, honestly, I'm more with Johnny on this one. Lovely is not exactly what I would call part 2. I'd say the word was interesting. I feel like in hindsight, after like stepping away from the computer for a while, I was like, that was an interesting problem. And I'm glad that I got to sink my teeth into it and run down a whole lot of weird alleyways that did not do what I wanted it to do, and then still end up with something. But yeah, I 100% agree with you, Miguel, here. Part 2 was hard. 100%. Here's another question. Quick question. Have you tried using Kotlin script files for the Advent instead of setting up the whole project with Gradle? I'll be quite honest with you, I have not. What I did try for a little bit, and what we also saw on stream, though, was Kotlin notebooks, which I thought strikes a very nice balance between the interactivity, the ability to visualize things, and still very good tooling support. So, if you, of course, I would be very much curious to hear what your experiences are if you try the Kotlin script files. But I have no experience with this one myself, to be honest. Is anyone else getting happier every day that they built out some grid util functions? It's probably the 8th day this year that I have written a Vector 2 class. But alas, you know, I never learn, or I enjoy the aesthetics of having everything that's relevant to this specific problem sit in the same file, so that I don't run into the same problem like Olaf did at some point, which was, you know, you have a library, but you gotta know your own library as well. I should remember to add a get operator with to my custom point2D class. There's a couple of things I think here you can work out. And I think Martin makes a very good observation, which is the puzzles are very 2D this year, but I can't recall if that's typical or not. I honestly also do not quite know. But I feel like this might actually be a great question to ask my guest for today. It is day 12, after all, the final stream, so I figured it would make sense to bring on someone who is very much intertwined with Advent of Code in Kotlin in general. Someone who, if you scroll through the Advent of Code Slack, you'll see his avatar pop up in a lot of the conversations, and who I believe has been doing Advent of Code since 2017, so probably has a pretty good idea of how 2D things are this year. So yeah, I am very excited to bring Martin on to the show. Hey Martin, how's it going?
Hi Sebastian, I'm very glad to be here.
I'm so happy. I'm really so happy to have you here because for us and for everyone behind the scenes, you are so directly intertwined with everything that's going on in Advent of Code and Kotlin. I think a lot of people, when they first check out the channel, they'll notice you like popping into the into the conversations that happen. And I think you've been doing this for a very long time. Correct me if I'm wrong. I think you also won one of the previous challenges for one of the previous Advent of Codes in Kotlin.
Yes, I am doing Advent of Codes since 2017, as you said. I never actually got in the first place on a Kotlin leaderboard, but I was recognized, I think, 3 times by JetFrames for being very active in the community.
Right, you got the community award. That's what it was.
Yeah.
So I am curious. I am just going to forward this question to you. How do you feel about the structure of Advent of Code 2024 in particular? You feel is it 2D? Is it difficult? Is it easy? Like what's the vibes from your perspective?
Yeah, it definitely seems like there's an above average amount of 2-dimensional grid puzzles, but but I'm happy about that because today was also a 2D grid puzzle, and they are very good for making visualizations, which worked out for me today. So I wanted to prepare one, so I'm not going to complain.
That's very exciting. So yes, you heard right. There is not just one visualization, but multiple visualizations that we will be able to check out later, which of course I'm already really looking forward to. And I also have a feeling that we're gonna have quite the conversation about this problem again. Like I alluded to beforehand, those 4.5 hours. I didn't just sit there and do nothing. I tried a whole bunch of things, and I ran into a whole bunch of very strange alleyways and hit my nose on all kind of weird things. So I am even more interested in how someone who's been doing so much Advent of Code might approach one of these puzzles. So I think we can just hop right in. And I'll grab the reading hat. Again, it has served me well even today. Today was one of those days where I decided I should get out of bed and actually, sit on my desk. I decided that probably after the first 1.5 hours or so to get to that actual result. And so I'd like to imagine the hat, it radiates a little bit of extra knowledge. So we're diving into day 12, garden groups. Why not search for the chief historian near the gardener and his massive farm? There's plenty of food, so the historians grab something to eat while they search. You're about to settle near a complex arrangement of garden plots when some elves ask if you can lend a hand. They'd like to set up fences around each region of garden plots, but they can't figure out how much fence they need to order or how much it will cost. They hand you a map, your puzzle input, of the garden plots. Each garden plot grows only a single type of plant and is indicated by a single letter on your map. When multiple garden plots are growing the same type of plant and are touching horizontally or vertically, they form a region. For example, this region. This 4x4 arrangement includes garden plots growing 5 different types of plants labeled A, B, C, D, and E, each grouped into their own regions. So we have some A's, then we have our B's, we have the C's, we have a single D, and we have 3 E's. In order to accurately calculate the cost of the fence around a single region, you need to know that region's area and perimeter. The area of a region is simply the number of garden plots the region contains. The above maps types A, B, and C plants are each in a region of area 4. The type E plants are in a region of area 3, and the type D plants are in a region of area 1. Just the numbers. Each garden plot is a square, and so has 4 sides. The perimeter of a region is the number of sides of garden plots in the region that do not touch another garden plot in the same region. The type A and C plants are each in a region with perimeter 10. The type B and E plants are each in a region with perimeter 8. The lone D plot forms its own region with perimeter 4. visually indicating the sides of plots in each region that contribute to the perimeter using dash and pipe. The above map's regions perimeters are measured as follows. So we have 4 A's, which means we get 4 segments above, 4 segments below, and 2 segments on the side, counting 10. And for an individual one, we have those 4 individual segments. Plants of the same type can appear in multiple separate regions, and regions can even appear within other regions. For example, here we have little islands of X's inside a large ocean of O's. The above map contains 5 regions, one containing all of the O garden plots, and the other 4 containing each a single X plot. The 4 X regions each have area 1 and perimeter 4. The region containing 21 type O plants is more complicated. In addition to its outer edge contributing a perimeter of 20, its boundary with each X region contributes an additional 4 to its perimeter, for a total perimeter of 36. Due to modern business practices, the price of fence required for a region is found by multiplying that region's area by its perimeter. The total price of fencing all regions on a map is found by adding together the price of fence for each region on the map. In the first example, region A has price 4 times 10 is 40, region B has price 4 times 8 is 32, region C has price 4 times 10 is 40, region D has price 1 times 4 is 4, and region E has price 3 times 8 is 24. So the total price for the first example is 140. In the second example, the region with all of the O plants has price 21 times 36 is 756, and each of the 4 smaller X regions has price 1 times 4 equals 4, for a total price of 772. That's 756 plus 4 times 4. Here's a larger example, which contains a whole bunch of regions, like the R plants with the price of 216, I 32, and so on. Adding all of them up, you get a total price of 1,930. What is the total price of fencing all regions in your map? Okay, that was a lot of text, a lot of numbers, a lot of letters, and definitely still a 2D grid. We can take a super quick peek also at what that puzzle input actually looks like if we zoom out a little bit. Wow, that really kind of looks like a map, but not too enormous. So Martin, I'm curious, what went through your head? Walk us through the thought process.
Yeah, the first thing I thought was, wow, that's a lot of reading for Sebastian to do on stream today.
Mm-hmm.
as we heard just now. And yeah, as I said before, I was quite happy to see a puzzle based on a two-dimensional grid. Quite like that. And as for the puzzle itself, the difficulty curve seems to be holding up. It was harder than previous days, but not a lot harder. At least that's how it felt for me. There's a lot to do in this puzzle, but nothing too crazy, I feel.
Okay, yeah. I mean, for the first part, I definitely agree. So let's take a look, and I'm gonna throw it over to your screen here, and you can give us a little bit of a tour of how you'd approach this.
Yeah. So before we get to the actual solution, maybe let's explain what my little utility methods are framework here, so we know what's going on here. So yeah, as you can see, I have this little solve method, which all it does really is just reading the input file and providing it to the lambda as a list of lines, and then the result of the lambda is getting printed as the solution. And then the first line is again an utility method that converts the lines to a grid. And what does this return? Because there's really two approaches to how we can represent grids in Advent of code. Because some people use like two-dimensional arrays or two-dimensional lists, or have a list of lists of values, and that works fine. But the other approach, which is the one that I use here, is to have a hash map from points to values. So this is what it returns. It returns a map from a point class or which is what you're calling vector 2, I think, in your project, to values. And yeah, I prefer that approach because it allows you to create like sparse grids for puzzles where not every point on the map actually has to have a value. It also makes it very easy to extend or add values outside of the initial grid without having to extend all of the lists. So yeah, so that's what's happening here, which is reading the input, creating a grid, and the solution is really split into two parts. Because the first thing we have to do before actually calculating what we need to calculate is to partition the grid into regions. So we need to find out which point or which garden plot in the puzzle belongs to which region. And only later, once we have the regions, we can actually calculate the cost of the fence we are using to fence it off. So the first part of the solution will be just trying to partition that grid. And so let's see how I did that. So first of all, we need a way to store it. So this is again a map from point to int, and it will assign a region ID, which is just an arbitrary integer I create, to assign which region a given point belongs to. And so how we actually do that is I loop through all of the points on the grid, and we only want to map each point to a region once. So the first thing you do is just check if we already have a mapping. If yes, then we just continue to the next point. And if not, then this point doesn't belong to any region yet. And so we'll increment our region ID because we are creating a new region now. And now what we will be doing is basically doing a flat fill algorithm from this point. So we have a to-visit list of points that we want to visit in our flat fill, and it's initialized with the initial point. And then we're just going to loop through that list until it's empty and remove elements from it. And when we remove an element that we want to visit, we check what plant is growing there or what character was there in the input file. And we check that it's the same as our initial point from the initial outer for loop. If it is, then it means it belongs to the same region. So we can update our region map and set the current point to belong to the same region ID. And now that we have a point that's also in this region, we want to look at the neighbors of this point. So I have another utility method here to get neighbors. It just returns a list of 4 points in the 4 cardinal directions from this point, which is the current point we're looking at. And we add that to our list that we want to visit. But of course, we don't want to visit that point twice. We want to visit it once, so we filter it so we don't have duplicates in our list. And also, if the neighbor already is mapped to some region, then we also don't need to look at it anymore. So we filter that out as well. And yeah, so we're going through the flat fill, adding neighbors, and assigning them to regions. And once this for loop finishes, we'll have a full region mapping where every point on the grid is assigned a region ID. So that's basically the first half of the solution. And now that we have the regions, we can actually calculate the fence costs. So the fence costs. So the puzzle told us that to do that, we have to calculate the area of the region and multiply it by the perimeter. So again, we are looping through all of the regions, and for each regions, we're just getting all of the points in this region. And we can imagine that each point or each garden plot is like 1 square meter, and so all we have to do is just check how many points we have, and that's the area. There's nothing really much to calculate here. It's a little bit more complex for the perimeter. So again, if we think about 1 point, it has 4 sides. So 1 point by itself will have a perimeter of 4, because there's 4 sides. But then if a point is touching another point, which is in the same region, then there isn't really a border between them because they're part of the same region. So we have to subtract that. So basically what we're doing is we're setting the perimeter of a point to 4 minus the amount of neighbors that are in the same region. And that's how we get a perimeter, the amount that a given point is contributing to the perimeter of the entire region. And once we sum up all these perimeters of all these points, we have the total perimeter of the region, and we can multiply it by the area. Again, sum up that, and that's the solution.
That is okay. I love that. That is very clever. I think so. There's a couple of parts here to this. I'll throw my solution on in just a little bit. But first of all, your floodful algorithm seems very canonical. Seems pretty reasonable. You start at a point and then you explore further, see which other points are eligible, and then continue flood filling those. That's a very straightforward way of clustering these. And then I really like the approach of doing this 4 minus. I think that's a very cool insight to have, like looking at an individual element or at like an individual square and saying like, well, it'll always contribute 4 unless it has more neighbors, and each neighbor steals one of the sides that it would contribute to the circumference. Very, very nice. Again, I'm always so impressed by how short these solutions can be, or like how concise the solutions can be if you put your mind to it.
Yeah, I mean, it's a really interesting thing about of course how different people approach or have different goals into their solutions, because some people like write like a lot of functions and make it very readable and have like everything is put down into small methods, everything is nice and tidy. But then it's more lines of code overall.
Yeah.
Like I'm mostly aiming for the solution to be concise, which is maybe not as readable at times. It's definitely smaller. But there's the balance there to have there, because I mean I don't want to be doing code golf and completely unreadable single liners. That's not nice either.
I mean, it looks like you're still giving things like vaguely reasonable names, which is already something that I can appreciate. This is here's a question from Martin, which is this already like a refactored, polished solution, or is this basically what you came up with this morning?
Yeah, it's definitely refactored. I wouldn't come up with this at 5 a.m. So. So yeah, my original solution was a bit more ugly, but it was the same vein.
Okay. Let me quickly throw up what I built here for a second, because I think it probably makes the most sense if we still have the context. I have a lot of code folding going on. I hope you'll forgive me for that one. One of the things that I did pretty much immediately this morning, which I did not do for previous ones, but the moment I saw the 2D grid, I was like, we're putting in checks. We're making sure that whenever I run this thing, I'll run it against any example before I even get something remotely looking like a part 1 solution. So my part 1, the first bit here is this is just kind of my parsing logic here. So getting out of the text, just get me all the coordinates, which just makes it a little easier for me to navigate through things or to iterate through things. This is just 2 stacked loops. It's nothing crazy. I think we've seen a function like this written a couple of times already throughout this advent of code. And yeah, then I also did a clustering based on essentially a variation of a flood algorithm, which is my find fensible plant regions function that also returns a list of fensible regions. These just happen to be like containers for like a bunch of coordinates, so it'll just have all the coordinates inside. I forgot the shortcut for recursively unfold. Folding expand recursively is Command Option plus. There we go. So I essentially also do a floodfill algorithm but somehow I ended up doing it backwards. So rather than starting with an empty list and adding new things, I start with all the coordinates that are in my grid. I'll pick one of them. I will assign that. I will essentially then find everything that's connected to this specific part, and then I will remove everything that I added to this specific group. Which, I mean, it's literally just running it in reverse, kind of. Yeah, and then here inside the actual find region for coordinate, this is the then more classical approach. We start with one vector, which is just one of the locations, and then we grab ourselves our locations to check, and we do a regular flood fill, which adds the up, down, left, and right. Now that I think about it, most likely I feel like I'm probably just doing a bunch of duplicated work here. But this is, from a logic perspective, I did not refactor anything since I wrote this in the original thing. I just gave things names and extracted a couple of functions, so it's a little easier to understand. But yeah, this is still, I think, pretty much the same flood fill, just with a whole lot more code. But of course, I would like to shout out that my patented get plant add function makes another appearance here. That just makes sure that I never hit like nulls, or I don't have to work with nulls. I can just assign some kind of default value, so that I'll never run into any kind of nullability problems, or I don't have to drag that along with me, which just made my life a little bit more convenient. So yeah, after all the coordinates have been assigned into some sort of region, into a fensible region, I just collect all of them into a list, which means that find fensible plant regions just gives me back a list of fensible regions. Which means now that if I hop back into my part 1, once we have all of those, we can map out the area, we can map out the perimeter, and then we can zip those two together. Of course, all of this could have been done in one step as well. But in my case, I just create both of them separately and then combine them together, immediately providing a transform. So this is immediately applied to each element, one of each from the areas and the perimeters, which then allows me to get the sum. The area is, I think, exactly the same implemented. It's just the size of coordinates that we have inside here. The perimeter, once again, this one's a lot of code for me. Not not because I was trying to be verbose, just because that's the one I came up with. Which, once again, hey, we're building a list, and we are just checking whether, but given an element that is part of our actual plot, or of our fensible region, if we can find an up, down, left, or right neighbor that is not part of our fensible region, then that would be part of like our boundary. That's where we would place our fence posts. So I just add all of those, and I get the sum out of that. And yeah, it's not the very fastest. It does run for like double-digit milliseconds, but it does get the job done eventually. Thoughts? Any obvious concerns?
Yeah, I saw that you want to be very adamant that your list is not a set, right? I think I comment.
Oh yeah. So yeah, it really is not. This is also, I think, one of the other points that someone had noted just a little earlier, was that maybe we could have just used the plants themselves as a region ID, which is also something which is very tempting. In my original version, there's also a note in here that specifically says, remember, you can have more than one plot of any given type.
Exactly. You cannot do it. It wouldn't work.
Yeah, exactly. So plants repeat, so we can't use them as IDs. Exactly. Yeah, but apart from that, I think besides my maybe slightly strange backwards flood fill with finding the coordinates to even get started with, I feel like there's not much that's different here. I wish I had come up with this 4- approach. That would have saved me a whole bunch of iterations again. But hey, it still got me to where I needed to go.
Yeah, and it's looking good, very readable.
Thank you very much. It does feel a little enterprisey. I don't know. It's a lot of function calls, but I have to admit, one of the things that I think made it immediately a lot more readable, at least for myself, and even like allowing me to reason about it a lot more, was introducing like a value class that has just a name, because I always find it a lot easier to assign meaning to a list of fensible regions than a list of vector 2, or then if you happen to work on some rows, it's like a list, and at some point I'm just out. This is a little bit a better approach. I also have to say I don't know what it is this year. I'm just using these list builder functions left and right. I think I could rewrite some of these certainly to also be more functional, maybe to use some maps or some filters, but I don't know. They're just kind of convenient every once in a while if you just want to quickly whip something up. So I find myself using them honestly more often than I'm used to, and I'm still trying to figure out how I feel about that.
Yeah, that they are certainly very useful. I agree.
Yeah, like they just for me they end up showing up in a whole bunch of places. Okay, so far so good. I think actually this would already be a pretty cool place to maybe take a look at what this looks like visually, since you already did prepare this wonderful little visualization. You wanna say a little bit about how you built this, with what you built this, how long it took you? I don't know.
Yeah, so this is built with Compose Desktop or Compose Multi-Platform. It's just a single window, simple desktop application. It's just currently showing the input file, the input grid, because this is just the test sample. It still works on the full input, but then it's a bit harder to see things. And yeah, it visually goes through the same algorithm that we explained already. So yeah, you can click the find regions link on the top right. It's going to iterate through the points, and from each starting point, it does the flat fill algorithm and tries to find all of the points that belong to that region.
This is very nice. How are you picking the colors?
From a list of 20 colors.
Okay. All right.
and just the index by region ID modulo site the list.
If you had casually just added like the 4-color theorem to this, I would have lost my mind. I will be quite honest. I was getting a little worried.
I thought about that, but I didn't want to take so much time.
Understandable. Yeah, like this is I mean this is really gorgeous, and I think it makes it a lot more approachable to kind of see what's going on.
So now we have all of the areas assigned, and you can see them in different colors. I also have a list of regions on the right. Now if you want to solve part 1, we need the areas. So if you click calculate areas, it's just going to go through every area and through every point and just count all of them. Which we don't actually need to do in the return. We just do dot type and it's there. But here we're actually counting them. Now we have the number of points in each area, and it was added to the list of regions on the right. Now the only thing we need is the perimeters. Now we can click calculate perimeters.
And I mean, yeah, like looking at this is like it just even by looking at the visualization, I'm like, wow, this is so much faster. Because I mean, obviously it just it does a little bit of math here, but it ends up giving us the 1930, which is exactly the values that we wanted.
Yes, exactly.
That's a super intuitive way of showing this. Really gorgeous, and I do love the design aesthetics also of kind of going with the vibe of Advent of Code here. Like that was a very nice choice. I find this very pleasing.
Yeah, I see that Martin is commenting that he thought of Minesweeper, which is just exactly what I thought when I was deploying.
Yeah.
It is basically Minesweeper because each point is just showing how many neighbors there are, how many bombs there are.
Oh yeah.
Around.
That's a great way of thinking about it, actually. Yeah, lots of praise for you here in chat. Yeah, even Olaf, whose visualization we're also gonna see a little bit later here, thinks this one's very impressive. So that's a high praise coming from other visualizers. That's very exciting. Yeah, and I can only say it's I can say the same. This is really gorgeous. Wonderful. Well, now I am very curious. I mean, if all of this went so smoothly, very nice, it wasn't so much of a problem. Where did my next 4 hours go? So, I think the reading hack goes back on, and we'll take a look at part 2. One of the good parts, at the very least, is that the description of part 2 is not just a single line that says "now run it 100,000 times."
That helps.
But we'll see if it's any better. And exactly, Jonathan, the hat emojis come back. That's right. We're diving into part 2. Fortunately, the elves are trying to order so much fence that they qualify for a bulk discount. Under the bulk discount, instead of using the perimeter to calculate the price, you need to use the number of sides each region has. Each straight section of fence counts as a side, regardless of how long it is. Consider this example again. The region containing type A plants has 4 sides, as does each of the regions containing plants of type B, D, and E. So A has above, to the side, to the bottom, to the left, and so do the other rectangles. However, the more complex region, containing the plants of type C, has 8 sides. That's this little Tetris piece that we have here. So we have 1, 2, 3, 4, 5, 6, 7, 8 sides. Using the new method of calculating the per region price by multiplying the region's area by its number of sides, regions A through E have prices 16, 16, 32, 4, and 12 respectively, for a total price of 80. The second example above, full of type X and O plans, would have a total price of 436. Here's a map that includes an E-shaped region, true, full of type E plans. The E-shaped region has an area of 17 and 12 sides for a price of 204. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That sounds about right. Including the 2 regions full of type X plants, this map has a total price of 236. This map down here has a price of 368. It includes 2 regions full of type B plants, each with 4 sides, and a single region full of type A plants with 4 sides on the outside and 8 more sides on the inside, a total of 12 sides. Be especially careful when counting the fence around regions like the one full of type A plants. In particular, each section of fence has an inside and an outside, so the fence does not connect across the middle of the region, where the 2 B regions touch diagonally. The elves would have used the Möbius fencing company instead, but their contract terms were too one-sided. The larger example from before now has the following updated prices. We have a whole bunch of regions summing up, like the R region summing up to 120, I to 16, and so on. Adding these together produces its new total price of 1206. What is the new total price of fencing all regions on your map? I did the one thing when I saw this morning, which I was not prepared for, which is I started doodling. And I started doodling on the back of an envelope because in absolutely no foresight whatsoever, my nightstand did not have any kind of scrap paper. So it was a whiteboard marker on the back of an envelope. I'm not sure if it helped, but yeah. So how was what were your thoughts? What went through your head when you read the second part?
Yeah, part 2 definitely looked and was harder than part 1. It's not as easy to calculate the number of orders now. So yeah, I was a little scared it will be too hard, but we did it in the end.
Okay, let's see what you've come up with, and throwing your screen back on here, and we can take a look.
All right. So yeah, same as in part 1, we'll need to partition the grid into regions and assign a region to each point. So this is exactly the same as we had in part 1. So nothing more to say there. But what is changing is how we are calculating the price of the fence. Because now instead of the perimeter, we need to count how many borders each region has. And the special property with that is that a border that is continuing through several points is counted as one border, even though it has a length of non-one length. So how I'm doing this? Well, again, I'm looping through all of the regions and getting all of the points in a given regions. And this is the easy part. We get the area, same as before, just the number of points. And this is the hard part, which is how to get the regions. And so here I have a direction enum. It's just an enum of the 4 cardinal directions, so north, west, south, and east. And we'll be going through each direction. So basically, we'll loop for each region. We are looping through the 4 directions, and then we'll be looping through all of the points in that region. So basically, looping through each region 4 times for each of the cardinal directions. So in the beginning, I want to find how many north-facing borders there are, and then how many east-facing borders there are. And so how we'll be doing it is we're looping through all the points of the region. We again have a list of visited points because we don't want to visit any point twice. But if we did that, then we continue. And when we have a region, we want to check if it is a border. So we have a direction, let's say north. And again, I have a utility method here, move. So point move direction is just returning a point moved one step in that direction. So if we're moving north, it's just going to have the y coordinate smaller by 1. So we move to that direction, and we check our region mapping to find what's the region ID of that other point, and if it's equal or not to the region ID of our current region. Because if it's not, then that means it's not part of this region, which means that we are at a border, right? So if we are not at a border, then we will just continue looping through the points. But if we are at a border, then great, we have a border, so we can increment our border count because we have found a border. And we added the visit points. And then we need to find out what other points form the same border, because we don't want to double count them. So here I just have a list of turns. So we have a 2-element list for left and right. And we take our direction and rotate it left and right. So when we were checking north-facing borders, we will be now going west and south. So we have 2 of these side directions, west and south, and we'll be going through points in that direction. So we're taking the current point and we're just in a loop. We're moving to that side and adding that point to our visited points. And we are doing that as long as we are still in the same region and as long as we are still on the border. So this is the same check as we did previously. And so the output of this loop is that we are just adding all of these points that are forming the same border to our visited points, which means that when we later encounter them in our alter for loop, we're going to skip them because we don't want to count them again. And yeah, this is how we find all of the borders for every direction. Now we only count each border once. And yeah, once we did that, we can just take the sum of all of the border counts, and we have all of the borders in the region that we can multiply by the area. And this is one solution, because once I did my solution, I looked at other people's solutions, and I thought that this is not the approach that most people do. I thought that many people were counting the corners of a region, because basically the amount of borders is basically the amount of the borders are between corners, right? So if you find all of the corners, you have found all of the borders.
Yeah,
so that's also one way.
So yeah. I really, okay, this solution is really nice. This solution is really, really cool. I'll tell you a little bit about the odyssey I went on. But I ended up once again doing your solution in reverse. I ended up doing it backwards, which once again made my my code explode in like size. It got there, but okay. So my original doodles, and also I think if I were to just hold on, give me 2 seconds here. If I would just were to go to Wikipedia, and I just look for polygon, I think somewhere in here is that the number of sides. I'm gonna try to find this. Yeah, like the Wikipedia page clearly states any polygon has as many corners as it has sides. Which is great because it also means it has as many sides as it has corners. That works in both directions. So we might have been able to use this. So my initial thought was like, okay, let's find some corners. And I started running. I was like, okay, how would I do this with a bunch of corners? And I think maybe the Mazes for Programmers book has maybe irradiated me slightly too much, because I was like, okay, the approach is pretty simple. We'll approach it the same way as we approach it a maze, as long as we can do this like right hand side rule, right? Where like if you have a maze, you can, and you like hold out your right hand, you run that like along the entire like length of the maze, you'll like hit the like entire circumference of like your polygon or your maze. It's like, okay, that seems like good enough. This gets kind of annoying very quickly. It's also wrong for this in its entirety. I'm gonna prefix this by this, but this also gets annoying when you start actually writing this code, because all of a sudden you realize that you may have situations like the E example. Hold on. Scrolling too fast here, like the E example. So I might be walking along the circumference of the E, and I might find myself just in a dead end. And now, I mean, now I can't just be like, okay, we'll keep track of where my right hand is and where I'm looking, and then like try to make a step, because I might step into a wall. So now I might have to take a left turn, but I might have to do more than one left turn at a time. So I was like, okay, that part doesn't work. Jonathan already knows that this does not work for another big reason here as well. But we'll get to that part. Again, my mind was clouded. I was pre-caffeinated. So I decided to expand like my brain. I was like, okay, I know of a trick. And the trick that you can do in theory is you can just zoom the entire thing by 3x. You can just make every square like 3 squares. And that by doing that, the layout, since the layout doesn't change, you no longer have dead ends. You only have like curves that you walk around, which would solve this problem, like the small problem of I don't want to run into a corner. So I spent a little bit of time doing that, And of course, immediately, because I decided to change too much of the code that I already had, I ended up messing up a bunch of my area calculation code in the process. Because all of a sudden, all the areas that I calculated are 9 times the size as before, and I should have just it did a separate data structure entirely. So I was like, okay, cool. I did a little bit more tinkering, and then I looked closely, and then I decided to do the thing that Jonathan is already screaming at his monitor at. Is I took a look at another example, like for example this one, where you very quickly realize that there is islands in your graph. Like not everything may be like just reachable with just a single like path by holding your like right hand alongside it. You might just do the outer loop and never get to like the inner parts at all. So that was frustrating. That wasn't great. So that's, I think, where the first like 1.5 hours or so went. But not to worry, because then out came the Google Sheets. So I ended up drawing something, and this, I think, is something that now with your already pre-explanation, we can kind of understand a little bit, which is, essentially at the end of the day, what I'm really trying to find are edges by, like, I thought of it as like lighting up the entire structure from like one angle. So if you like approach it from the top, then like you get all the top edges, right? If you approach it from the bottom, then you get all the bottom edges, and so on. I was still in a 3x zoomed mindset here, which is why all of these are 3x3. But then I quickly realized that that's not even necessary anymore. It's just that if I am this white square, and I know that I have a neighbor which belongs to my group, then I know that this square happens to be an edge. And then, of course, you still would need to like merge adjacent edges. Like, for example, here, those 2 or 3 blue edges that belong together, you would still have to do the same. And that's what I meant by doing it in reverse from your solution. You're starting inside the figure, and you're looking upwards to see if you're part of the edge. I did the slightly wackier way of drawing a bounding box around the entire thing, with extra space, like a larger bounding box, and then looking inwards in each direction, which does also work, but your code's a little nicer. So we'll take a look at my part 2 here. The areas, the regions, and the coordinates, all of those stay the same. Once we figured out how to do the prices, that part also stays the same. There's nothing particularly interesting here. The magic happens in the extension function or the extension property sides for a given region. I can unfold that one, and then I can scroll to the top. So here, the idea is just the following. We draw ourselves a bounding box that gives us at least 1 square extra space in each direction from all the coordinates. That's just so that we can check from all sides whether we could potentially be a fence. And then we can iterate through the edges. And we need, at least in this approach, we need to do this in a way that only looks at one direction at a time. It's a very bad idea to try and optimize this by moving, for example, horizontal bottom and top edges into the same list of coordinates, because then afterwards you will just merge all of them into one virtual fence line, which is not great. So you end up writing out four loops. It's not beautiful, but I get to stack 2 build list functions inside each other like a madman. So here we iterate, first of all, by we grab ourselves the horizontal top edges, which is just we go through each line, and then we take a look at each position in those lines. And if we are not in the coordinates, but we find something below us in the coordinates, then we are part of a top edge. And then we just ply the entire thing backwards, or we essentially just like do it in the other direction. So we check whether above us we have a something that's part of our plot, and then we iterate through the y coordinates on the inside and the x coordinates. So now we're looking at it from a columnar perspective, and we're just adding those coordinates, whether they're right or left. It's a lot of like boilerplate-ish code here, and I could have also rewritten this. Like I had a version that I wrote earlier today that rewrites this into like xrange.map, yrange.map, but I genuinely thought that that actually did not particularly aid readability. So I decided to keep it this way. So what do we have at the end of this? We have lists of vector 2. So we have lists of rows that have maybe potentially one or more contiguous groups. So now we just need to actually count those contiguous groups. I'll say that it's not actually necessary to do it the way that I did, which is like actually physically instantiating all the groups and then seeing how many you have. You could have just kept count. But this was at a point where I had been staring at this problem for 4 hours. So I was like, I'm going to write out the solution that's obvious to me, rather than trying to do a micro optimization here. So yeah, this essentially just goes through. It grabs itself, or it starts by having like a collector collection, just somewhere to put all of our groups. We loop through our lists if they happen to belong to the current group, which means their distance to the next element or to the previous element is less than or equal to 1. Then we continue adding to the current group, and if that does not happen to be the case, that means we are further away, so we start a new group, and we just add it to that. And to finalize, we also make sure we don't accidentally lose like the last group if it does not happen to be empty. And also, of course, this is the point where I was like, I mean, at this point, you throw in like a tiny Manhattan distance, because you're like, I'm already in this deep. I might as well just calculate the distance based on just both parameters, even though we're only looking at things that are on exactly the same line. And that gives you a property called sides, and then you can use that to do area times sides and get a price, or get the sum. Which was a journey. Any comment?
Yeah, I mean, this definitely works. But yeah, I think you added some extra work for yourself by going through the outside rather than from the inside.
Yeah.
But yeah, that's my approach that works.
I think this is, if there is one thing that I have learned throughout our Advent of Code streams, but to be fair, I think I end up relearning this every single year. A very important skill, and something that I would like to get better at times, is looking at a problem or at a sub-problem from a different direction. I very much like the approach that we had on one of the first days with Dave Leeds, where he just rotated like an entire matrix rather than like changing the way that he would look for patterns. And I feel like this is the same thing. It's if I had spent a little bit more time staring at this problem, rather than like just immediately going like, I know a way of calculating this, and instead going, I feel like there's maybe more than one way of calculating this, it probably would have helped me immensely here.
I feel like I feel like rotating it is a good idea. If you could rotate the entire grid, then you only need to find sides like on one side 4 times, which is going to be 4 different sides with rotations.
Yep.
That's a good idea.
Yeah. So rotating it, or like just like you did, interpreting it like in the other direction. And of course, then the other part was maybe having a little bit too much hubris in the beginning and going like, oh, I know how to go through this through this grid to find some corners, because there was something, again, like after discussing this with a couple of colleagues who like doing things like, you can just kind of look at like the two like neighbors, like the diagonals, and the direct neighbors, and you can already make some inferences on whether something's a corner or not, and all of a sudden all of this code like collapses down to also like 15 lines of a bunch of like if statements that just check a couple of neighbors. And it's not that I didn't have the like I had the awareness that what I was looking for originally was corners. I made that connection, but I did not capitalize on that knowledge here. So that's something for myself to learn and probably attempt differently next year or whenever a problem like this presents itself. I very much appreciate this lovely comment here. You're not alone. I've been on a journey down very long paths too. Yeah, I feel it. I feel it. Oh, and others use something like breadth first search walks to walk left and right along a fence until it ends, then count it and move to a new fence. Also, very cool. So again, I've said this a couple of times. This year's Advent of Code has done an excellent job at providing problems that seem to have a whole bunch of different solutions that people can discuss about. It's very, very rarely is it that people just produce the exact same thing.
Yeah, and it's very cool to see. There's just thousands of people solving exactly the same problem, and yet every solution is different. And even if someone takes the same approach as you, the code is still different, and you can just learn so much from that.
Oh yeah, absolutely. I do think that I've also learned that I should probably start next year's Advent of Code maybe with having like a couple of utility functions for working with 2D grids. In particular, I think I would have had a slightly easier time if I did have just like a rotate function or like a transpose or whatever like that. That I feel like that could have come in healthy every couple of times. Or maybe I just throw it into a like computer vision program next year, and I'll just run an actual corner detector. I don't know, run a Gauss kernel over it, something like that. Who knows?
Yeah, there were people in previous years just throwing the problem into some automated algebra solvers and coming up with the answers. So yeah, that is certainly an approach.
Which is, yeah, that's so lovely how you can just optimize along a bunch of different axes here. And of course, I suppose going from here, we can also take a look at how we can visualize this.
Yes, so what we're missing for part 2 is calculating the borders. So what's going to happen here is, as I said, we're going to iterate through all of the regions 4 times per region for each cardinal direction, and then every time we find a border, we're going to walk along that border in the to the left and right, and assign it to one border. So yeah, you can click calculate borders, and we can see it happen.
I love the highlighting. That's incredible. Yeah. Gorgeous. Now imagine having to draw an entire bounding box around this every single iteration and trying to do this from the other side.
Yeah, that would be harder to visualize.
Ever so slightly, yeah. But again, like this is a really good visualization of what's like actually happening. I love the you can see how it iterates it direction by direction, looking at each side, and then determining the borders like that. Oh, that was like the little four times.
Yeah, the single point region is very fun.
Very satisfying. This is a very good payoff after all this hard work. It's a lovely little thing to look at. And look at that, we got the 1206. And now it looks even more like Tetris.
Yeah, we can see the number of borders now on the list of regions on the right and on the outer. And yeah, this does look a little bit like Tetris, but it's definitely not 4 points per region.
Not quite. This is going to be extra hard mode for Tetris, I think. No, this is really gorgeous, and of course, thank you so much for also taking the time to prepare a visualization for this. Is this something that you do like somewhat regularly?
This is the first one this year, but I did do a bunch of visualizations in previous years to show around. So yeah, it's not my first one.
Very nice, very nice. And of course, I think all of that is also part of your GitHub repository. So if people want to see how that is created, they can also do that, which is nice.
Yeah. The code for the visualization is not as nice as the section.
Oh, that I can believe, but I feel like that's often the case for a lot of us. I mean, we've taken a look at one of the visualizations on a previous stream, and it was just an instrumented version of the same algorithm, which ended up with a whole lot of extra code in places where you don't expect it. But yeah, I'm also going to link that one briefly for people if they do want to check it out, which is very, very elegant. Now, since Martin's also hanging out in the chat, and he did also provide a little visualization, I would, of course, be remiss not to throw that one up on screen as well for a second here. We'll see that it is quite a similar approach. I can zoom out a little bit here. We also have our nice little test input here, and we can run our part 1 solution. A little zoomier approach, but also a very satisfying color palette. I do enjoy that one quite a lot as well. And we also have the part 2 solution, for which I think I need to reset the contents, and that one just does the immediate kind of the border creations here. So thank you, Martin. No, don't worry. It's not a competition. I mean, Advent of Code is for some folks, but we're all here for different purposes, and I just appreciate you taking the time and sharing this with me. Yeah. Paste your real input. We can try. But that one, it's not a very nice thing to do for the visualizations. I think that one might be a little harder. But why not? We can take a quick peek and see, put it to the test here. Just grab my real input, and I'll throw that one in here, and we'll rerun this. And here's our visualization. There we go. And then we can, for example, find our regions. Okay.
Yeah, and helpfully I included that hover to speed up thing, which
yeah, it certainly does help. But yeah, look at this. It's really like, again, it's just kind of gorgeous to see see it work on a larger data set as well. I like that it's kind of cutting off the individual letters. It makes it kind of look like height markings or something like that. Or
the points are a bit too small to show the letters.
Yeah. But this is still very, very satisfying.
And also the list of regions is not scrollable, so we just cannot see them. But it's still fine.
Fair enough. I'll be honest with you. I feel like this gives me enough of an overview of the regions that we have here. I'm not sure there would be any wild insights that I'll be able to gain from the regions that are lower down there. Yeah, very, very nice. And in fact, we even have one more visualization after this, provided by Olaf, which is awesome. Looks like medieval Germany on a map. Honestly, I can kind of see it. Like those are the Crusader kings, like feudal states, all the tiny little kingdoms and so on. Yeah. Pop quiz: when would this puzzle be useful? That is an excellent question. I don't know, Martin. Do you have any any thoughts on this?
Yeah, I know at least one application of it that will be useful. It will be useful if you want to get on the Advent of Code leaderboard.
There we go. It's a good thing to learn a little bit about the flood fill algorithm and twisting and turning things in your head. That's what it's good for here. Simulating rising sea levels and water running into land. That's also an interesting way of thinking about it. Different height maps. And then I guess you already know how much the dam is gonna cost that you have to build to keep the water out. Huh. Good point. Good point. Yeah, that's a literal flood fill. Appreciate that comment, Martin. That's a good one. Yeah, so we also still have, let me just grab my my last little visualization that I have here, which once again, this one comes from Olaf Gottschalk, who joined us a couple of days ago. So if you haven't seen that one yet, I feel like I should give this that's a little too bright, black page. There we go. That looks a little better. There we go. So this one also does the nice little flood fill by regions, which I think looks quite gorgeous. I'm loving the little squares. This one kind of reminds me of like war games or like, that kind of era. And then we're calculating all the border positions. Okay. With a total fence price in dollars, that's a lot of money. And there's a discount available in part 2. So first we look at all the north fences. Look at that. Then all the east fences. I guess that's a pretty similar approach to what we've seen today. All the south fences. And all the west fences. And it's much cheaper now. At under $1 million. Look at that. And look at that. It even comes with a little sign-off. Thanks for watching Advent of Code in Kotlin. And that's exactly what I'm going to say now as well. Martin, thank you so much for joining us for this very last stream of Advent of Code.
Yeah, thank you for having me, and good luck to everyone for the rest of the puzzles.
Yeah. Once again, if you enjoy those puzzles and you'd like to keep going, I would very much encourage you to also join the Slack and join the Advent of Code channel, where there's a whole bunch of folks, most likely the people you've been hanging out in chat with, who are posting things, who are discussing things, who are showing off their solutions, exchanging tips and tricks. So take a look there and, keep it going. Keep enjoying those puzzles. And of course, our Advent of Code in Kotlin campaign also continues. Not with the live streams, but the leaderboards are still out there. The templates are still out there. If you haven't tried out Amper yet, I very much encourage you to do so. And of course, you can still win prizes by tagging your repository on GitHub using AOC 2024 in Kotlin. 870 9. So yeah, thank you, everybody, for being a part of this wonderful campaign of 12 days of live streams, 12 days of getting up at 5:50 in the morning for me, and then 12 hours later starting these streams. I really appreciate that we in the Kotlin community have something where we can come together, where we can exchange our each other with ideas, with like new approaches, where I get to learn something every single day, and I hope that you do too.
Yeah, it's all about learning in the end.
Yeah. So there are 13 more puzzles that will come up in the next one in 10 hours and 40 minutes. So there's going to be a whole lot more puzzling going on in Advent of Code that is so wonderfully also sponsored by JetBrains. So thank you so much. Really do appreciate it. And I hope that I'll be able to catch you on the Kotlin YouTube channel at a later point. So make sure you hit that subscribe button. New videos are already in post-production, and you don't want to miss those. So make sure you tune in there. So once again, thanks, Martin. Thank you, everybody who decided to tune in. Have lovely holidays and an absolutely amazing Advent of Code. Thank you, and
Thank you.
take
Bye.
care. Bye-bye.